Hello, and welcome to today's webinar, Enhance Your Analytical Scale Purification Performance with an Advanced Preparative Solution, presented by Mike Miller of Neopharm and Darcy Shave of Waters Corporation. Here's a quick guide to using the ON24 console. In the top left corner, there's a Q&A box for you to enter any questions you have during the presentation. Below that is our resource list where you'll find material relevant to today's presentation. On the top right is our speaker bios for more information on today's speakers. And finally, on the bottom right is a survey we'd appreciate you taking to get your feedback on today's presentation. Our first speaker today is Mike Miller of Neopharm Boston, based in Milford, Massachusetts. Mike has worked for Neopharm for 4 years and has over 10 years of chromatographic and mass spectrometry experience. At Neopharm, he works performing HPLC and SFC separations at both the analytical and preparative scales. My name is Darcy Shave, and I'll be your second speaker for today. I'm a Principal Product Manager at Waters Corporation, also based in Milford, Massachusetts, responsible for our purification, both LC and SFC systems.
Good morning, everyone. My name is Mike Miller, and I'm a principal scientist with Neopharm Boston. I'm here today to talk to you about using the WAPS system and its capabilities and leveraging those for scaling UPLC methods to prep. I personally have over 10 years of LCMS experience dealing in the analysis of molecules sub 100 Daltons all the way up to hundreds of thousands of Daltons. I use my diverse experience to help take on customer challenges here every day at Neopharm Boston. We are a chromatographic CRO, and we have analytical and preparative capabilities. We started as Verrica Discovery in 2007, and in 2016 we were purchased by Neopharm Labs and have transitioned into the name Neopharm Boston. Our core services include scalable purification of APIs. We do physical and chemical properties using tailored methods, method development and qualification. So if a customer comes in needing a customized method, we can bring that through validation and then transfer it up to our GMP site for validation. And we also do a lot of impurity isolation for structural determination, where we work with the customer using our high-res mass spec data and NMR to help come to a structure to help them figure out whether or not their impurities are detrimental to their formulation. So when I'm running prep, I always have the prep triangle in mind. We always need to know how much we can safely load on a column to not have any detriment effect to our separation, how fast we can push the method and still achieve the same level of separation, and then what level of purity we're shooting for and how it can drive the other two. At the end of the day, when I was learning prep, my boss told me, look at these 3, pick 2. And those are really what you can focus on. But really, all of that works within constraints. And I think one of the biggest ones is your system. And today we're going to be focusing on the Waters WASP system and how the benefits we get out of it can be leveraged into running more efficient methods that have been scaled up from UPLC methods. I've been using a WASP system for a couple of months now, tackling different types of separations. I've purified various small molecules, peptides, and oligonucleotides. The key highlights, I think, of the system are the fact that we have 2 ARC HPLC pumps going at 10 mils a minute at 9,000 psi. This higher pressure is going to let us use smaller particles. In conjunction, at this flow rate, we're typically running 10 millimeter ID columns of various lengths. And this size format is really nice because we can use a column heater without having to worry about heating the mobile phase. All of this is going to let us run smaller particles and longer columns, which will let us have higher efficiency separations and scale up from UPLC with a lot less scaling factor. So we're not going to be turning 5-minute methods into 45-minute methods. Later in the presentation, I'm going to revisit a presentation I gave about purifying liraglutide, a GLP-1 analog on the WASP system. Since we were talking about the column oven heating, this system is really good for when you're purifying something like biomolecules, where you may not have a lot of it, but you want that higher efficiency for your separation. In this case, we really took advantage of the column heating to help disrupt higher order structure in the liraglutide, which we observe by the increased temperature giving a later retention time, likely unfolding the liraglutide into a more linear state. But for now, let's focus on small molecule separation. What we're looking at now is a UPLC separation of my in-house test mix that I use to assess columns and systems. We're going to use it as a basis for scaling up methods, but I thought I'd just take a second to talk about pumps. When I encounter problems, most of the time it's a pump problem. So when using a system with multiple pumps in series, I would recommend having methods to assess the pumps together and individually so that you can save yourself time and not worrying about that later on. This UPLC separation of a basic compound, slightly polar neutral and a neutral compound, gives good separation between the peaks and has some small impurities that I can use for resolution calculations when needed. If I wanted to take my in-house UPLC method and convert it to a traditional HPLC method, we'd have to scale up the column. When looking at the efficiency of a column, formula we need to use is L over dP, or the length of the column divided by the particle size. For a Waters Acuity BEH 1.7 micron, 2.1 ID by 50 millimeters, we have an almost 30 L over dP. To get that equivalent separation, we'd need to be using a 4.6 by 155 micron. If we are to use the Waters gradient calculator, so this is a tool that Waters has that lets you easily scale up methods, to run the same method from UPLC to HPLC, we're going from 3.5 minutes to 36 minutes. This is almost a 10x increase in runtime. And what we're going to try to accomplish is using smaller particles on prep so that we can develop quicker prep methods from our analytical UPLC methods. So if we wanted to take that initial UPLC method all the way to a prep column, like a 10 millimeter ID 5 micron at 150 millimeter length, we're still going to get the same method times that we did with the 4.6 ID. Since we're keeping the L over dP the same, we're going to have the same program. However, by increasing the inner diameter, we're just going to need to increase the flow rate so that we get a scaled, consistent linear velocity so we can get the same separation. This still means we're looking at a 10x runtime. Whether we're starting with an existing method or developing a new method to scale to prep, we're typically starting with linear gradients. To save time in the case of scaling a UPLC method to prep in the traditional sense of a 19 by 150 millimeter 5 micron column, one tactic was using focus gradients. By calculating your %B from your linear gradient, we can hone in on that by quickly ramping to maybe 5% before its elution target and holding it to 3% after, and then quickly ramping to wash conditions. Typically, we would keep the same %B per column volume to maintain the separation, but you could flatten out your gradient by time, but there's a couple of caveats to that. As we've seen, and as we will continue to see, when you scale UPLC to traditional prep, we get a multiple factor of increase in retention time. By flattening that gradient, we're only going to increase the method time even longer, and we're also going to get broadening of peaks. As you can see in this example, a ballistic gradient was ran on a 2.1 by 30 millimeter UPLC column. To achieve the separation in prep, that was scaled to a 19 by 100 millimeter 5 micron. And you can see right here that we've gone from a 3-minute method to a 15-minute method. This was successful in scaling and isolation of the target. It's very clean after being isolated. However, we're losing on time. And what we're trying to get to today is scaling UPLC methods to quicker sub-UPLC prep methods to save on time. So let's take my initial UPLC gradient of my test mix. Another tool Waters has is the Focus Gradient Calculator, which allows me to input all my system parameters. I can fine tune the percent focusing before and after, which I typically keep at 5% before the target percent B and 3% after. And when I wanted to scale it to a 19 by 150 millimeter 5 micron method, we've now taken a 4-minute method up to 20 minutes. So a 5x increase in runtime. We get this increase in runtime because we're limited by our equipment. Traditional HPLC pumps, I typically don't bring above 4,000 PSI. If we wanted to run longer columns, we had to sacrifice our particle size so that we could have low enough back pressure to not overpressure them. But now that we have a system where we can go to 9,000 PSI on prep, we can start to look at smaller particle columns. A couple of years ago, Darcy and I worked on using the Waters Auto Pure system for scaled oligonucleotide purification. So I had a couple of these 2.5 micron columns laying around. Using the 10 millimeter by 50 millimeter 2.5 micron column, I've now turned my initial UPLC separation into a 6-minute prep method. This is only an increase of about 50%. And I'm only seeing that because since we have a slightly larger particle size from 1.7 micron to 2.5 micron, to keep a consistent L over DP, I would have needed a 75 millimeter column, but I only had a 50. So here on the top, we can see my original UPLC separation. And on the bottom, I have now run the same test mixture on the WASP system with the slightly increased runtime. I have the 3 components pointed out, and as you can see, the resolution is quite similar. Taking a look at zooms of the baseline, we can observe some of the impurities in this test mixture. And we can see when I scaled from my UPLC to my prep that we are still observing resolution of these impurities between the major peaks. I wanted to apply everything that we've talked about so far to an actual sample. So what we're looking at now is the UPLC separation of a commercial pesticide. In the bottom left-hand corner, we're looking at a baseline zoom of the front region, showing that there is a complicated level of impurities in there. We're currently ongoing with this project and trying to get better separation of these impurities so that we can scale this method to a WASP prep method and isolate them, and then we're going to come back and QC them by this initial method. But from this initial UPLC separation, if we were to bring it right to prep, again, we're looking at a 2x runtime, which when thinking about traditional scaling to prep is not that bad. We began this presentation talking about the prep triangle and how the constraint of equipment can really drive your separation. By leveraging those WASP system pumps that can go to higher pressures and working at scales that allow us to effectively heat our column, we can run smaller particles and potentially longer columns. We can easily scale up UPLC methods to more efficient prep methods using tools provided by Waters like the gradient scale calculator and the focus gradient calculator. Scaling UPLC methods to higher efficiency prep methods will save us both time and money, especially when it comes to challenging separations like oligos and peptides. So higher pressures and temperatures, letting us run smaller particles for more efficient scale-ups, really dealt with the speed aspect of the prep triangle. So now let's look at load and what we can do with smaller particle sizes. I wanted to know, does decreasing your particle size affect your loading? And how much can you load on a 10 by 100 millimeter column? To investigate these questions, I came up with a simple loading study. We're going to look at same column size of 10 by 100 millimeters, and we're going to investigate these in 3.5 micron versus 5 micron particle size. We're going to use a single method for both columns, and we're going to use a different test mixture consisting of a basic compound, an acidic compound, and a neutral compound. So what we're looking at here is the full chromatogram of my entire loading study done on the 3.5 micron column. In the beginning, we have propranolol. In the middle, we have ibuprofen, which is actually the small peak around 4.2 minutes. And then we've got transtylbene oxide. This is why I don't use this mixture as my in-house test mix, because I've noticed that with certain mixtures of compounds, I get interactions. Let's look at propranolol on our acidic method loading study. Propranolol is a base, so under acidic conditions, it's going to be charged and therefore quite polar. And we see this reflected even in the lowest point on our curve right now. The 4 mg per mil is already tailing. As we load more and more into the column, we can see each time it's pushing forward a significant amount of time. And it's only until we get to 64 mgs that we're at any kind of significant increase in peak height. Propranolol, being a base and charged under acidic pH, means it interacts with our nonpolar stationary phase of C18 less. Now we're looking at ibuprofen, which is an acidic molecule. This is loading a lot better. From the get-go at 4 mg per mil, we're getting a much more symmetrical peak shape. But as we increase, we're starting to get that shark fin as it pushes forward and saturates the phase. On the bottom, we're looking at a separate injection series I did of singular ibuprofen at the same concentrations as in the mixture, because in our mixture, we had an interfering peak that was more intense than the ibuprofen. But we're going to actually use this later to our advantage in looking at this data. Now we're looking at our last compound. Transtylbene oxide is the most nonpolar of the three, elutes the latest, and also has the most symmetrical peak shape. Holistically looking at all the data, I compiled the data points that I thought to be the most relevant. Looking at the 16 and 32 mg per mil in the region between that interaction peak, the ibuprofen, and the TSO, we can start to pull out the answers we're looking for. At 16 mg per mil, we are still getting almost baseline resolution between ibuprofen and that other peak. At 32 mg per mil, we're starting to lose it. The green and red represent the 3.5 micron column, which looks like it's slightly less intense and pushing forward a tiny bit. However, when considering prep methods, I'm looking for major changes that are going to seriously impact what I'm doing. So at the end of the day, with my pretty basic study, I've concluded that I don't see much difference between 3.5 and 5 micron. From my loading study, I've determined that you can probably safely load about 10 to 20 MIGs on column. However, I try to push it a little bit and just repolish compounds when they don't meet spec. So let's apply some of the theory that we've been talking about to an actual separation. Purifying liraglutide on the WASP system was very easy. We developed an analytical separation, we generated a focus gradient from the linear, performed a loading study, and then we scaled to prep and took some cuts. So the top chromatogram is my linear gradient of liraglutide on BEHC18 with ammonium acetate at pH 8. On the bottom, we can see my optimized focus gradient, with the white region being the area that was stretched out from the top chromatogram's white region. With my optimized focus gradient at analytical scale, I performed a loading study to see how the separation changed when I put more on column. Using the XIC in the mass spec for the ion of the impurity front running on the liraglutide, we're able to see that as we loaded more on column, these impurities pushed forward as well. So we just kept loading more. On the top here, we're looking at my analytical scale, and on the bottom, we have the prep trace from the separation of liraglutide, where I put 4.5 MIGs on column. Performing separations and doing some really cool cuts of your peak is really easy when you're using the fraction links in the MassLink system. I purposely chose to take small cuts across my peak so I could assess the purity of them individually. Is any part of the peak more pure than the rest? And as you can see across my fractions, I get varying purity, with the heart of the peak being the most pure. When coming into a separation like this, you need to define your spec, and that will determine your productivity. Because if I was fine with 95% pure, I could combine more of my fractions and do about 5 MIGs per hour. If I needed a higher purity spec of like 97%, I would only be getting about 2.5 MIGs per hour. The long run times of the liraglutide purification were because it's a complex separation and we were still using 5-micron particles. Had we leveraged the higher pressure and gone to a smaller particle size, we could have probably decreased that runtime maybe to 15-20 minutes, which would have improved our productivity by threefold. As I mentioned at the beginning of the presentation, we were also doing oligonucleotide purification on the WASP system. Here we leveraged the higher temperature to help disrupt the higher order structure of the oligonucleotide, but we didn't leverage pressure here either with smaller particle size. Still running 5 micron, this was about an hour-long method. If we were to switch to smaller particle sizes, we could also be getting better resolution on the impurities that elute before the full-length product. With also purifying your full-length product, you could be going after impurities to then use as standards in the future to help quantify the amount left in your purified product. As you can see from this zoom of the baseline region of the oligonucleotide separation, there are a complex amount of impurities. And while we know these to be majorly failure sequences, if you needed to isolate one to use as a standard or to do structural identity on to figure out what it is because it's coming up at too high of a percent in your crude synthesis, by leveraging smaller particles, we could be getting better resolution between these and getting more efficient separation and isolation. So today we discussed using the increased pressure and elevated temperature limits of the WASP system to effectively and efficiently scale up UPLC methods to quicker prep methods. I spoke about how I've also used the WASP system to purify biomolecules like peptides and oligonucleotides, and how they would have benefited from leveraging the smaller particle size limits of the system. as they were hour-long separations, which could have been done much faster. I'd like to thank Waters for asking me to speak to you all today, and for you for your attention. Now I'm going to hand you guys back off to Darcy.
Thanks, Mike. Once again, I'm Darcy Shave, Product Manager at Waters Corporation. And I'm going to talk in a bit more detail about the new system that Mike did all this great work on. Before I begin talking about that new system specifically, I'm going to spend just a couple of minutes here making sure everyone understands what a purification system is. The setup for an LC purification system is identical to that of a general liquid chromatography system, with the addition of a fraction collector. The sample mixture is injected onto the chromatographic column, and the components are separated based upon specific chemical or physical properties. As the components are detected, they can be either diverted to waste or collected for further experimentation. The process of collecting the eluent can be as simple as an analyst who manually collects components as they elute, or fully automated, where the detector signals a fraction collector to divert the flow to collection vessels. Purity of the isolated fractions diverted to the collection vessels depends on the resolution of that compound from the other closely eluting impurities in the separation. Here's an example of a prep separation. It looks the same as something done analytically, except we've collected those peaks that are shaded. This could be an injection of milligrams or of grams of sample. The big takeaway message here is that prep is defined by intent. Prep or semi-prep is generally thought to start with 19 millimeter ID columns and go up to 50 millimeter or bigger, with flows from tens of mils a minute to hundreds of mils a minute, or even more. Some systems can pump at even liters per minute, but prep can be done at smaller scales too. You could be using a 50 millimeter ID column flowing at 200 mils a minute, or a 2.1 millimeter ID column flowing at 0.2 mils a minute. If you're collecting a fraction, you're doing prep. Waters has prep systems that flow up to 300 mils a minute and can be used for a wide range of column IDs. We also have a very good fraction collector, the WFMA, for prep work at analytical flow rates. What's missing is a system optimized for the space in between, the 10 millimeter ID column. Our systems work there, but are not optimized. We just heard Mike talk about his work on our new 10 millimeter ID prep columns. Before we talk about the system we released in support of those columns, I want to call out two numbers here, the reasonable flow rate and the reasonable injection volume. I'll mention those again later. As Mike mentioned, this new system is called the Waters Analytical Scale Purification System, or WASP system. We designed this system in collaboration with customers and users like Mike, along with our colleagues in our chemistry organization. What we heard from users is that the instruments and techniques used for the downstream testing of the compounds have become more sensitive, and so they don't need as much purified material as they have in the past. We've also heard that collecting low-level impurities has become even more important than it has been. This new system, in combination with new columns, was made to help with both those situations. We can now take advantage of the same benefits that analytical analyses have seen from using smaller particles. We're seeing the increased speed, sensitivity, and resolution that was first seen over 20 years ago when Waters introduced Acuity UPLC. Other improvements in the system make it easier to scale up from analytical work, helping increase recovery and yield. The narrower peaks we are seeing lead to fractions being collected in less solvent, directly resulting in faster dry down times, reduced solvent use, and reduced waste disposal. All this combines to increase productivity and decrease operating costs. Now I'll go over the components that make up a WASP system in a bit more detail. For those of you familiar with our LC auto purification system, you'll see a lot of similarities with a few big differences. I'll start with the pumps. As we saw in the chart I showed earlier, the optimal flow rate for a 10 millimeter ID column is about 7 mils a minute. And with the 3.5 micron particles, we can expect to see back pressures of 6 to 7,000 psi. For pumping at those conditions, we chose to use two ARC HPLC quaternary solvent managers. The flow of these pumps is combined, giving us a flow rate of 10 mils a minute and up to 9,500 psi, well above what we need. Next up is the 3767 sample manager. This liquid handler does both sample injection and fraction collection. The benefits of using the 3767 in this system are centered around its capacity. Its large bed can hold lots of crude samples and a lot of purified fractions. Another part of capacity to consider is injection volume. The 3767 has a variety of injection loops and syringes, so you should be able to find one that suits your workflow. The loops go from 20 microliters at the smallest up to all the way up to 25 milliliters at the largest. I don't think you'd ever use 25 milliliters on this system, but you could if you needed to. The system does ship standard with a 1 mil loop and a 1 mil syringe. Going back to that earlier table, 100 microliters is a reasonable injection volume for these columns. And because this is prep, we may want to inject even more to overload the column. So the 1 mil loop works great in these situations. Remember, we're never going to do a full loop injection. That would lead to sample loss. We're always doing partial loop injections, so we want to center that injection in the sample loop. But before we move any further, I would like to briefly discuss at-column dilution. This is a technique that enables an improved loading of samples that may be dissolved in a high concentration of organic solvent, resulting in improved sensitivity, narrower peak shape, and better resolution. The system would be configured very much like it is now, but the flow from the two pumps would be combined just before the column instead of just before the injector. Here's what we can see when we combine flows before the injector. As mentioned, a strong solvent such as DMSO can improve sample solubility, resulting in a potential increase in the column capacity. Unfortunately, large injection volumes of these strong solvents can distort the chromatography, resulting in a reduction rather than an increase in the amount of product that can be successfully isolated. Distortion occurs when strong solvent is carried from the injector to the head of the column as a plug sandwiched in a stream of aqueous solvent. Sample precipitation can occur at the edges of the plug where the strong sample solvent is diluted with the aqueous solvent. This precipitation can result in a blockage in the fluid path and lead to high pressure system shutdown. With larger injections, the volume required to dilute the sample can only be derived by moving the plug a substantial distance along the column. In such cases, the sample is deposited as a broad band that occupies a large fraction of the column volume. The result is an incomplete peak separation of peaks spread over large volumes of eluent. In an at-column dilution system, the system is reconfigured so that the sample plug is carried to the entrance of the column, where it is continuously diluted with a stream of aqueous diluent. The rate of transfer into the column is so high that precipitation cannot occur. The sample molecules are then absorbed to the packing material as a very narrow bands that can be eluted as well-resolved small volume peaks. System ruggedness is improved with at-column dilution since the sample has limited ability to precipitate in the loop or at the column head. Improved resolution between sample components permits increase in the sample size and thereby reducing the number of injections required for isolation. In practice, with at-column dilution, the column loading can be increased by 3 to 5-fold. The incidence of high-pressure shutdowns is reduced and column lifetime is extended. Here's the other big difference in this system with the auto purification system. Because of the flow rate and column size, we can now offer column heating for your prep separations. The CM30S is a single zone column heater that can hold multiple columns with diameters up to 10 millimeters and lengths up to 30 centimeters. It also operates at temperatures between 20 degrees Celsius and 90 degrees Celsius. This allows you to scale up any analytical methods without having to redevelop them at room temperature. This is a big benefit for any separation, but especially for oligos, which separate better at those higher temperatures. After the column, we have to split the flow. For chemically destructive detectors such as an MS or an ELSD, a portion of the flow coming from the column must be split from the main flow to go to the detector for fraction triggering. Since the detectors must detect a peak before the fraction collector is triggered, i.e. the delay time, the split flow must arrive at the detector before the main flow stream arrives at the fraction collector. To accomplish this, the split flow velocity is increased by using a makeup pump and makeup solvents. For this system, we're using a 100-to-1 splitter. That means that 99.9% of the flow is going to the fraction collector and 0.1% is going to the detectors. Or to put it another way, if we assume the flow rate is 10 mils a minute, just to make the math easier for me, 9.99 mils per minute is going to the fraction collector and 0.01 mils per minute is going to the detectors. Since the peak has to hit the detectors before it hits the collector, we do two things. The splitter has a delay coil, which is specially knitted to almost negate any band spread. This delay coil delays the flow to the collector, and then we add a makeup pump to speed the flows to the detector. This very robust split technique is one we've been using for quite some time successfully on our auto purification systems. In this system, the makeup pump is an isocratic solvent manager, or ISM. The ISM adds pulse-free delivery of an MS-friendly mobile phase solvent to the detector flow path, allowing acceptable amounts of dilution to occur before the sample enters a mass detector, while also speeding the peaks to the detectors. After the splitter, the similarities with an auto purification system continue. The system comes standard with a UV detector, whether that's a PDA or a TUV, and a QDA2, our newest compact benchtop single quad. For those requiring triple detection, you can also add an ELSD to the system. Just for a little more background, I'm going to quickly go over both UV and MS-based collection. In a UV-based system, we are not as specific with our collections because most things will absorb at the wavelengths that we're going to be looking at. So while we'll get good separation, we'll get a nice collection, but we'll pretty much collect every peak. Whereas mass spec detectors identify a separate sound pound, and so we can program in the mass of interest of the fraction that we want to collect, and so we now collect just the fraction, just the peak that we've targeted. It is important to be able to take full advantage of these different techniques, so we have developed software to do just that. As you can see from the slide, none of the detectors in this example actually saw everything, and so sometimes it is important to be able to use the intelligence of the software together with the detector capabilities to give the best possible collection results. The system is controlled by MassLynx using the application manager FractionLynx. FractionLynx manages and automates your sample purification processes. It allows you to tailor your system to your specific compound and laboratory needs with flexible compound detection, fraction triggering, and collection capabilities. FractionLynx is also compatible with OpenLynx Open Access to provide a simple walk-up purification solution. OpenLynx Open Access application called OA Login is a comprehensive, easy to use, and flexible walk-up solution for this system. I could spend this entire webinar talking about just the capabilities in our FractionLynx software. I don't have time for that today, so instead I'm going to give you a very brief talk about some of the key benefits. You have a choice of collection modes, whether it's time-based or peak-based. Peak-based collection uses the signal intensity threshold and or the slope from your chromatogram. Multiple detector signals can be used together to trigger fraction collection, applying the AND, OR, NOT, XOR logic, or mixed triggers. You can also have a number of different patterns to collect within. Sequential allows for a continuous collection of fractions in one tube after another. 1-for-1 collects the fractions for a sample in a single location, simplifying the spatial relationship between the sample and the fraction layout. Reserved tubes is similar to 1-for-1, except you set aside a certain number of collection tubes for each sample. One of the important features available within FractionLynx software is a capability called Auto Purify. Auto Purify allows you to automate your purification processes. Simply start with your analytical run and the software can create a sample list based on the results, with appropriate methods targeting your compounds of interest, and push that sample list to the WASP system for purification. When the purification is done, an analytical sample list can be created and pushed to your analytical system, enabling easy analysis of your collected fractions. Our analytical and prep systems are easily integrated with robotics, so you could have a completely hands-off system doing this work. If your lab is not quite ready to use robotics, we still have software that makes these systems easily accessible to the bench chemists. Included with every purchase of FractionLinks is a copy of OA Login, our walk-up software. It allows you to perform routine purifications more efficiently as chemists run their own samples, leaving instrumentation experts more time to focus on advanced analyses. Results at your fingertips are given with reports that can be automatically sent via email or viewed in the OpenLinks browser or printed. And its quality control capabilities help your administrators maintain peak system performance. Mike already talked about narrow methods a little bit, but I just want to reiterate what he said. One of the ways that AutoPurify helps you run even faster is with using these narrow gradients. Narrow gradients are more focused gradients compared to a generic 595 gradient, usually only covering about 10% composition change in the mole phases. The solid green line shows a generic gradient. The narrow gradients are denoted by the different colors, each one focusing on a different section of the chromatogram. AutoPurify will pick the narrow method that best suits your compound of interest based on the analytical run, and then use that method for purification. Here's another way to visualize these narrow methods. The start and end time for each gradient is the same, thus ensuring that the column is always at the same initial conditions before the run commences. Here's an example showing the benefits of a narrow gradient. With the generic gradient on the left, we don't see a good separation of the co-eluting peaks. However, when we do the same separation with a narrow gradient, we do see the separation of those peaks. Now I'm just going to quickly show you some data from this system run on the smaller particle columns. This data has been covered in some webinars and app notes we've had in the past couple of months, so I'm not going to go into any details. Here's some warfarin, which was used for the timing test. There's not a lot to see here, but I did want to point out that this was done with a custom pack 2.5 micron 10 millimeter ID column, running at 10 mils a minute and 7,000 PSI. Next up is some liraglutide work. Here was some of those initial loading studies, just so we can understand how much material we can put on the columns. We're collecting a lot of fractions across the peak, so we can see what parts of the peak are most concentrated. We see injections of 100 microliters of two concentrations of samples, 5 milligrams per mil and 0.5 milligrams per mil. Here's another example showing the purification of a degradant of a small molecule. The top chromatogram is the analytical separation, followed by the prep separation. The bottom chromatogram shows the analysis of the purified degradant. This final example is of a synthetic oligo. We've overlaid two chromatograms. The black trace is a traditional oligo column, while the purple trace is from the new Premier column. You can really see a difference in some of those early eluting impurities. And if you're looking to collect those impurities, the Premier column will be the one you want to use. To wrap up, in response to our discussions with customers about their changing workflows and purification requirements, Waters has introduced the Waters Analytical Scale Purification System and MaxPeak Premier OBD columns in 10 millimeter ID. Combining these two releases will help you achieve high capacity collection in smaller scales. The sub 5 micron particles, now available with these 10 millimeter columns, gives you faster chromatography, better resolution, and improved sensitivity. These narrower peaks reduce solvent usage, dry down time, and the amount of waste to dispose of, saving you money and boosting your productivity. Thank you for your time, and have a good day.
Thank you for attending today's presentation. Now we will proceed to the live Q&A portion. Please stand by as there will be a moment of silence before the transition. Thanks, Mike, for a great presentation, and thanks everyone once again for attending. We have some really good questions come in, so let's just get right into those. I think the first one here is for Mike. because you're the main user, or you're one of the main users of the system so far. What do you think are the main benefits of using this new WASP system?
So definitely the main I think the biggest benefit is the higher pressure, which allows us to use smaller particles. And I like being able to easily heat my columns to, decrease the pressure and denature large molecules.
Excellent. Good. Maybe a question for me was what types of applications are supported by this new system? Or maybe Mike, you could, after I go, you can try it. If you have anything different, you can add to it. I'm going to say there's not really anything newer. The applications you can use this system for are the same ones that you're using a higher flow, or 19 millimeter or 30 millimeter columns on those higher flow systems. We introduced this WASP system more because customers have told us that they need to purify less material. So now we've made a system that's good for purifying, again, milligrams, ones of milligrams instead of tens or hundreds of milligrams of system. So pretty much any application that you can do on your current LC system, on your higher flow prep LC system, you can do on this one. I don't know, Mike, you got anything to add to that?
I see it enabling me to maybe do low scale impurity isolation more efficiently with the higher efficiency columns. Like if I don't need NMR and I just want to get HRMS on my target, it's very easy to collect, a small amount of a sample of a sharp peak that I can just go to my QTOF with.
Good point. Yep. Here's one question specifically, Mike, about some of the data you presented. What oligonucleotide length were you looking at in your application?
Yeah. In the data that we presented today, it was a 20-mer, but using any of the Waters app notes, lots of good information by Martin Galar, you could definitely scale up or scale down any of the prep work he's shown to be done at 19 millimeters. I would also recommend maybe going and trying hexammonium acetate for better resolution. And since we're running at lower flow rates, running HFIP TEA on this is a little more amenable. I know I wouldn't want to do that on a 19 ID column just because the mobile phase cost would be astronomical.
Yeah, good point. Here's a question for me that's very related to that, because you did that work on a lot of that work on a 2.5 micron 10 millimeter ID columns. Someone asked, where can they get those? So those aren't on our website. Most of the columns that we sell, you can order from our website. Those 2.5 10 millimeter ID columns aren't available through our website. For those, you would have to talk to your Waters chemistry account manager, and they can we'll get those custom packed for you for people who want to do those sorts of things. Another question is, does the system support UV-based and MS-based purification? What about the mass specs? What among those are supported? So again, much like our LC auto purification system, you can use a PDA to do, if you want to do PDA-based peak collection, or a single quad, either of the single quads we have. I think in my slides, I only really talked about the QDA2, but the system does also support the SQD2, our slightly higher resolution single quad. Beyond that, we're still sort of investigating how some of our higher ed mass specs would work. So I can't speak to any of those right now. But yes, you can do UV and MS based both with this thing.
So I suppose a follow-up to that, Darcy.
Sure.
Sorry to interrupt you, but I think in some of the images shown for the system, it's shown with the triple detection with the ELSD. Could we do collection off the ELSD as well?
Oh, good question. Yes, you can. So UV, PDA, ELSD, or a single quad. Any of those can trigger fraction collection. Or using the mixed triggers, you can use them in conjunction with each other. So you can really target your collection to what you need to do. Good question. And then maybe, Mike, we can end with one question for you. How easy is it to use this WASP system? Is it any different than go ahead.
I was going to say, it's just as easy as using the regular Waters auto purification system. Maybe a little bit more maintenance with the second pump, but MassLynx is pretty easy to use. I think it's very user friendly, very amenable to walk up walk-up system that you could program for your lab. I highly recommend it.
Excellent. Thank you. So we're done a few minutes early, so I'm going to give everybody back 10 minutes in their day. So again, thank you, Mike, for presenting your excellent data, and thank you everyone for attending the webinar. Have a great day.